Welcome to the problem-solving set on pedigree analysis. Question 1 states that Sarah and Mark are both healthy individuals planning to have a child together. Sarah's mom has cystic fibrosis, a rare recessive disease. Mark's parents are both healthy, but his father is a carrier of the CF disease allele. What is the probability that Sarah and Mark's firstborn child will be affected with cystic fibrosis? Drawing a pedigree chart may be helpful. So I've gone ahead and filled out a pedigree chart and we can fill it out together. So the top line are the grandparents, and here this is Mark, and here's Sarah. So let's fill out who actually has the disease, and we will shade their bubble in. So it says Sarah's mom is affected with cystic fibrosis. So Sarah's mom over here, I'm going to shade her in. And because it's a rare recessive disease, we know that her genotype must be little cf, because it is recessive, so in order to have the disease, you must have both recessive alleles. Now let's see, it says Mark's parents are both healthy, but his father is a carrier of the CF disease allele. So we know that Mark's father is big CF, little cf, because they told us that he was a carrier. Now for the genotypes of the other two grandparents, because the problem states that cystic fibrosis is a rare disease, we assume that anybody in the problem who doesn't have the disease and isn't told to be a carrier, that they don't have any recessive allele for this disease. So Mark's mother must be big CF, and Sarah's father must also be big CF. Now let's see, Mark and Sarah are both healthy, so we're not going to shade them in, because we know that they're not affected with this disease. But let's figure out what their genotypes are. So Sarah, if her father has two big CF alleles and her mother has two little CF alleles, that means that she must be heterozygous, big CF, little CF, because her mother can only pass along the little CF allele. Now Mark, his mother has two big dominant alleles and his father is heterozygous. So he has a 1/2 chance of being homozygous dominant and a 1/2 chance of being a carrier or heterozygous. And that's because his father can make two different gametes. So half the time he will pass along one allele to his gametes and half the time he'll pass along the other. Now the question finally, it says, what is the probability that Sarah and Mark's firstborn, which is designated by this question mark, will be affected with cystic fibrosis? Now in order to be affected, again, this child will have to be little cf. So it's asking, what is the probability of this? Now Sarah, as we know, there is a 100% chance that Sarah is a carrier because her mom is affected with cystic fibrosis. And there is a 1/2 chance that Mark is a carrier because his dad is also a carrier of this disease. So if Sarah and Mark are both carriers, then it would be a simple monohybrid Mendelian cross, and that would mean that there's a 1/4 chance of the child being affected with this disease. So because all of these conditions have to be true, Mark has to be a carrier, Sarah has to be a carrier, and then they both have to pass their recessive allele on, you're going to multiply these probabilities across. So again, there is a 1/2 chance that Mark carries this recessive disease allele. There is a 100% chance that Sarah carries this recessive disease allele. And if these two are both carriers, there is a 1/4 chance that their child will be affected with this disease. So if you multiply that across, 1/2 times 1 times 1/4, you get a 1/8 chance that their child, designated by the question mark, will be affected with cystic fibrosis. Question 2 states, if two parents are heterozygous for dimples, a dominant trait, what is the probability that they will have a daughter with dimples? Now this question may seem like it should be in the monohybrid section, but they're actually asking about two traits. They're asking about the gender of the child and also this dimple trait. So let's write out the genotypes of the parents. So both are heterozygous for dimples. So it could be big D, little d, and big D, little d. Now I don't think you covered this in theory yet, but most everyone knows that a human female is XX for her sex chromosomes, and a human male is XY. So these are the parental generations. Now it's saying, what is the probability that they will have a daughter with dimples? So in order to have a daughter, that daughter must be XX. And the probability of having XX is 1/2. And that's because the mother can only give X's, and the father half of the time can give an X, and half of the time can give a Y. And the probability of having dimples, because it's a dominant trait, the offspring would just need one dominant allele. So we can write it as big D dash. And that is just big D little d times big D little d, which is, again, a simple monohybrid cross. So the probability of having the dominant phenotype is 3/4, which we've gone over and over by now, so that should be pretty simple. The probability of having both of these things be true is 1/2 times 3/4, so the probability for each separately, and that equals 3/8. So that is the probability of having a daughter with dimples. Problem 3 says, for each of the following human pedigrees, indicate whether the inheritance pattern is recessive or dominant. Give the genotypes of affected individuals and of individuals who carry the disease allele. So the way I like to do pedigree problems is look for some simple things that will make you guess either dominant or recessive, and then going through and writing the genotypes to make sure that your initial guess is actually the right answer. So there are two things in this pedigree, pedigree A, that scream out to me that it is one or the other. So first, you see affected individuals in all 3 generations. So that's my first clue. My second clue is that every affected individual has an affected parent. Now these 2 clues make me guess dominant. So this is my hypothesis, if you will. Now let's go through and see if it really is dominant, what the genotypes would be. So if the trait is dominant, that means that unaffected individuals will have 2 recessive alleles. So let's say the allele is A. So any unaffected individual would be little a, little a. Okay. Now with these, you know through some of the parents and the children what other genotypes can be. So let's look at the first individual in generation 2, right here. This individual is unaffected, and one of this father is unaffected. That means that the mother must be heterozygous because it needs to get this other little allele from someone. So let's guess that this mother is heterozygous. That way she has one dominant allele, which would give her the affected trait, and she could pass on this little a to her son. By the same token, if you cross a heterozygous with a homozygous recessive, that means that the second individual here in generation 2 must be heterozygous as well. And the same goes for the family on the right. If they have an unaffected individual here, that means that this parent must be heterozygous, and this individual must be heterozygous. So, if you're crossing 2 heterozygotes, they both have the affected trait because they have one dominant allele. And all of their offspring, except for one, have this trait. So all of these affected offspring have at least one big A. So because they have one unaffected child, that's consistent with crossing a heterozygotes. If one was homozygous dominant, then they would never get an unaffected child because they would pass on this dominant allele to all of their offspring. So this works. And also it says indicate the genotypes of all affected individuals and of individuals who carry the disease allele. So for these, the offspring in generation 3, you can't really tell if they're homozygous dominant or heterozygous. The only way that you would do that is if you got the data from their meetings and see how their offspring come out. So you can't tell that from here. But all of these genotypes are consistent, and so I think we should say that this is definitely a dominant allele. For pedigree B, there are 2 characteristics that stick out in my mind. So when you look at it, you see that the affected trait skips generations. It's not seen in every generation. And also that affected individuals can have unaffected parents. So as you see, from generation 1 parents, they have an affected child. So these two characteristics tell me, to make me guess that this is a recessive allele. So let's guess that first, and then go from there. Also, just to take note, this double line here, that means that it's a marriage between cousins. So if you travel back up, they actually have a family connection. Okay, so if this is a recessive trait, that means that the genotypes of these affected individuals would be little a, which means that both of their parents must have at least one little a. But because the parents are not affected, then they must be heterozygous because they don't have the recessive trait. And the same goes for the parents down here. So with this, it seems that zeta works, that this is a recessive trait. But let's try and see if we can find any carriers. So it's not definite, but let's see which individuals may possibly be carriers. If these two parents on generation 1 are heterozygous, that means that this child may be a carrier, or it may also be homozygous dominant. Now, a lot of times in pedigrees, especially when the affected individuals, there's only 2 in this whole pedigree, you want to assume that the trait is rare. So anybody who is marrying in, like this individual or this individual, you assume that they don't have this allele unless they're actually affected. So they would be homozygous dominant. So all of these individuals in generation 3 are definitely carriers because their mother only has this little a allele. Here, this individual is coming from outside of the family, so again, they would be homozygous dominant. Now, this individual here could be a carrier. Let's write it as that, or it could be homozygous dominant. And then this individual down here could be a carrier, or it could be homozygous dominant. So the data does support the fact that this trait is a recessive one. Again, for pedigree C, there are 2 characteristics that should stand out to you, and that is that there are affected individuals in every generation, and also that every affected individual has at least one affected parent. So here, your guess is going to be dominant. So again, let's go through the genotypes to see if our prediction is actually true. So if it's a dominant trait, that means that any unaffected individual are going to be recessive. So that means this is little a. Again here. Okay. Now let's look at the second generation. So these are the offspring of the first 2 parents. If some of these offspring are unaffected, that means that the original father must be heterozygous because they have to get their second recessive allele from somewhere. So by that token, anybody who is affected in this generation 2 must be heterozygous because their mother can only give a recessive trait. So these are heterozygous. For the first set of offspring in generation 3, that means that this individual that is affected must be heterozygous as well because their mother is homozygous recessive. And for the individuals in generation 3 on the right, these individuals that are affected must be heterozygous because, again, their father is only homozygous recessive. So this data is clear that it is dominant, is its dominant trait. And again, you want to take notice that the trait is seen in every generation, and every affected individual has at least one affected parent. Problem 4 says that phenylketonuria is a recessive genetic disorder that affects an individual's metabolism. 2 normal or healthy parents have a child with phenylketonuria. What are the parents' genotypes? What is the probability that the next child will have this metabolic disorder? So again, take note that this is a recessive genetic disorder. So we can define that as, so it's PKU, that's the symbol for phenylketonuria. So say to be affected with that, you have to be little p, little p. So it's asking if a child is little p, what are their parents' phenotypes? I'm sorry, genotypes. We know that their phenotypes, they're both healthy, they don't have this metabolic disorder, but what are their genotypes? So this would be F1. And in order to get little p, that means that each of the parents must have at least one little p. And we know because they're healthy, that means that their other allele must be the big P. So both parents are heterozygous for this gene. It says, what is the probability that their next child will have this metabolic disorder? So again, in order to have this disorder, you have to be little p. And if you cross this is a simple monohybrid cross. The chance is 1/4 of getting little p. So that is the chance that their next child will have this disorder. Problem 5 states that spinal muscular atrophy is a recessive disorder in humans. A couple wanting to have a baby is concerned because each parent has a sibling with muscular atrophy, though they and all 4 parents are unaffected. So I went ahead and drew a pedigree for this scenario, and I want to fill out the genotypes together. So remember that this is a recessive disorder. So that means that these 2 individuals in the second generation that do have this disorder are homozygous recessive. So let's call the allele A. So they are both little a. In order to have both an affected and an unaffected child, the parents in this first generation must both be heterozygous. Big A, little a, big A, little a. And the same goes for these parents. Now you know they must be heterozygous because they do pass on the little a allele to their affected children, but they themselves are unaffected, so they must have this dominant wild-type allele. So, we don't know yet the couple in question here and here. We don't know their genotypes, so let's just leave that blank for now. They definitely need to have at least one big A because they themselves are unaffected. Okay. So part A says, what is the probability that the female partner in this couple is a carrier of the atrophy allele? So it's this individual right here. So the question is, what is the probability that this female is heterozygous or a carrier? So let's do the monohybrid cross of her parents to see what the possible outcomes are. So let's do a simple Punnett square. We have big A, little a, and big A, little a. So the offsprings for this parent could have been homozygous dominant, heterozygous, or homozygous recessive. Now you know that this female is not homozygous recessive because she doesn't have this disorder. So we can cross out this option. That means that there are only 3 possible options left. So the probability of being heterozygous is 2/3. So that's very important because otherwise we said the probability of being heterozygous would be a half or 2 out of 4. But because we know that she's not little a, the probability is only 2/3. So that is the answer for A. Now B asks, what are the chances that their child will have this muscular disorder? So the child is represented by this question mark. So we'll say, what is the probability of the question mark individual being little a? So in order to have that, both parents we know have at least one big A. So in order for them to pass on and have an affected offspring individual, that means that they both must have this little a allele. So we already found out in part A that the probability of the female individual being a carrier is 2/3. By the same token, because it's basically the same genotypes in this family 2, there's also a 2/3 chance of the male in this couple being a carrier. And if both male and female of this couple were carriers, then there would be a 1/4 chance, which is a simple monohybrid cross probability, of the child being little a, little a. So if you multiply that across, you get 4 over 36, or 1 over 9. So that is the probability that this individual, represented by the question mark, will have this disease. Okay, now part C asks, what is the probability of their child being a carrier of the mutation? So what is the probability of the question mark individual, their child, being a carrier, which is big A, little a? Now there are two possible ways that this could happen. If this individual's parents were both heterozygous, big A, little a, and big A, little a, then we know that there is a 1/2 chance of the child being heterozygous. However, if one parent was homozygous dominant and the other was heterozygous, then there's a 1/2 chance of the offspring being heterozygous. So because either scenario can give the outcome that we want, we have to do the probability of each separately and then add them together. So let's do this scenario first. The probability of both parents being carriers is what we did before. So there's a 2/3 chance of each being a carrier. And if those were both carriers, then there's a 1/2 chance of the offspring being heterozygous. So that equals 4 over 18, or 2 over 9. The probability for this scenario. So for one of the individual parents being a carrier, we know that that probability is 2/3. By the same token, we know that the probability of them being homozygous dominant is 1/3. And I'll just show you that cross again up here. When you cross the grandparents, this is the Punnett square that we did. Now we know these parents are not affected, so we cross out little a, little a. So now there's a 1/3 here chance of being homozygous dominant. So if both of them, if these are the probabilities, then there's a 1/2 chance of the offspring being heterozygous, or a carrier. So if you multiply that across, that is 2 over 18, or 1/9. However, this scenario, let's say this was the mother and this was the father. There's also another scenario where the father is homozygous dominant and the mother is heterozygous. So these probabilities for this would be the same as this one here. So what we're just going to do is times that by 2. So it'll be 2 times 1/9 is equal to 2/9. So this takes into account that it could be either the mother or the father that is homozygous dominant and heterozygous for the other one. So the total probability, including these 3 scenarios that could give the probability of the child being a carrier, you just add them across. So it would be 2/9 plus 2/9, and that equals 4/9. So that's taking into consideration anyway that the individual offspring can be a carrier, and that is the total probability.